what they want to ask you is, and it's very simple. So let's move on, and I'll provide an example of that. So let's move on. Okay, now here we have expected values. So let x be a discrete random variable having a probability mass function f of xk, and then you have k goes to n, right? The expected value of x is defined as mu, and that's sums, that's kind of like a weighted sum, or a weighted average. The variance of x is defined by this, yeah. So notice how this is a lot different. Something like this is a lot different than something like this, right? Even though the same quantity, but they're different. You could say different mechanics or computation, because they're the same quantity but different computation. Why? Because in this case, for a discrete random variable, what happens is you're going to be given a table of values or something like that, where you have f of x, k, and then you have xk. And basically, what you're going to be doing is this has some kind of value associated with it. K, this has to be same quantity type. So let's say if we were talking about money, right? So yeah, if I diversify and invest in 4 different options, basically saying, well, what's the probability that I'm going to get profit from this? You could say it's 10%. So then the next thing you might say is 0.05. If I get profit from that, what's the probability I get profit from that? Is $5, and then I say $5 or something like that. And I don't know, these aren't necessarily entirely logical, but if I invest $100 in that, then and from this idea, I might be saying something like, so then from this, my expected value of my investment is going to be 0.1 times 2 plus 0.05 times 5 plus 0.001 times 100. I'm not saying I made it a good decision. I'm just writing this out. Plus 0.01 times 50. So that would end up being $1.05. So I'll just put this over here. $1.05. So this is what we should expect from that investment. And basically, let me be clear about what this means, because I'm not saying that you're putting in $2 or $5. I'm saying that this is what it's worth, and we're saying this is the probability that I'm going to get profit from that. I'm not saying that this is going to get a certain percentage of it, but just basically that I'm going to get profit from it. So if you say, okay, well, the probability that I'm going to get profit from is 0.01. If it was 100% profit, if the chances that you got 100% profit, then obviously what you put in is what you're going to get, is what you're going to earn back. So that would be the example I'm providing. And similarly, you're looking at it like that, you're looking at the variance like that as well. And now that might seem like a very strange concept, but let me emphasize that these, in our example, this would be the probability of a profit for xk, for k. So hopefully that made sense. And so you're going to expect to get, this is how much we're going to expect, is $1.05 based on those current conditions. Anyways, let's move on. So in example 5.5 and 5.6, we're going to use that basic principle, which is that we're looking at similar quantities. That's our first filter, and hopefully it works. So let's say we have a study that has a sample size of 5, a standard deviation, which may not be relevant, a standard deviation of 10.4. Now, is that a standard deviation? Let's see if that even needs. That probably implies population, because the other one says and a sample standard deviation of 11.6. What is most nearly the variance? So because we see here that we want the variance and it doesn't say the sample variance, then we know it means the population variance. See, sigma squared. So obviously we just take what's similar and we use it. So that's just variance is equal to 10.4 squared, which gets us about roughly 110. So that's the answer. Simple, right? Because when we see that we were scanning for our first filter, which is just the fact that it was, similar in quantity, then we got our answer. So anyway, let's move on. It says, a study has a sample size of 9, a standard deviation of 4, and a sample standard deviation of 4.2. What is most nearly the sampled variance? So the sample variance is, like we said, okay, let's see what we can do about this. We have a sample standard deviation of 4.2, and we want the sample variance. Okay, well, that's easy. Just take the variance squared, and that's going to be equal to the sample standard deviation, because this is sample, right? And they're similar quantities, right? And we're going to square that. And so then that's just 4.2 squared, which is about 16, right? Or 18, I think. Yeah, about 18. And by the way, I actually got this one wrong when I was studying for it. And I just started realizing, I'm like, why not just have a simple filter for these types of problems? Which is the fact that you just have similar quantities. That's really easy, because they realize we're not statisticians. We're just engineers trying to make it through. So anyway, hopefully that helped. And yeah, it's really easy. Sometimes, like I said, there's certain examples where you would need to use the number of the sample size or some population size. I don't even know if it would be a population size, but some kind of amount, and in some cases you would have to do that, but it's if it's, remember, go through the first filter and just see if it is okay. So without further ado, we want to anyway, I'm glad that they gave enough information on these problems, so let's go ahead. And so now we're moving on to linear regression, which is a very hot topic in statistics, but it's also a very mind-burdening and overbearing concept, because you're always going to be trying to calculate this thing and that thing and putting things together, and it's going to take forever to do it, and you're doing it almost for no reason because you could just use a calculator. So anyway, let's go ahead and see what that's about. So I'm pulling this from my statistics book as an example. And so all we have to use is the calculator to determine what this is. So let me read the problem. Good forecasting and control of pre-construction activity leads to a more efficient use of time and resource construction projects. Data on construction costs in $1,000 and person hours of labor required on several, whatever, it doesn't really matter, presented in the following table and are taken from the article blah, 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 blah. Each value represents an average of several projects, and 2 outliers have been deleted. So now the problem is compute the least squares line for predicting y from x. Okay, so basically all you have to do, the question is basically that we want to find y of x, and then that'll be a line, obviously, right? But we don't know what that is yet. And basically, the idea is that you have a bunch of points that's relating to cost and person hours. And it's, if you were to plot everything and sort of get an average, you would get a line that's like this, to average lines that would go through. So this would be your y of x, and it's a linear regression approximation. And so if we were to just use the calculator, because you can use the calculator to achieve this, it's be much better off. Please see my video to see incoming videos for full results. What you want to do is you want to go to data and put in all your numbers. And in this case, there's about 20 sets of numbers. So I went ahead and did everything already. And so now you go to stat and then keep going down, stat reg, and then to linear, because in this case it's just linear regression. It's just number 4. This is ax plus b. So now I put it in L1 and L2, so I went ahead and said, okay, good, no, and then just go to calculate, and it gives you everything you need. So you have a equals this, b equals that, r equals r squared, that's the coefficient, whatever. You want to see how it relates. So you have all these numbers, right? So clearly, this is just all you need for ax plus b, right? So let's go ahead and put these numbers in. Okay, so now that you saw that video, it's clearly just a matter of looking at the calculator and realizing it's in the form of ax plus b, which just simply means that it's that your regression line is, in this case, is 0.695x plus, and by the way, this should be minus 235.3, and that's going to be in, I think it's in dollars, right? Yeah. So then that'll be the answer for this problem. And it's that simple. I mean, you could verify it using all these equations, and I could show you what that is on the next slide. See, you could use all these equations, but it would be insane to do that, to calculate the same thing. So hopefully you're starting to appreciate just how powerful the calculator is for doing FE type problems. So anyways, let's move on. So like I said, you could have also used all these different equations, which are very time consuming, but that would have taken a lot more time to determine what basically your approximation is, which is just this. That's the approximation. And that, because notice how this is A hat, B hat, right? And in this case, A hat and B hat are these. And A hat and B hat use Y bar, X bar, and B hat itself. So, and S, X, and X, these complicated expressions. And this is just totally overbearing. Look at this. You would have to sum all those data points up, and that's like 20. Why go through the computational stress if you could just use the calculator? So the parable / moral, use calculator. It'll save you a lot of time. Well, I already did it, so. So now we have Chapter 5 continued. Confidence intervals for the mean mu of a normal distribution. So now this is actually somewhat important because it's something that I couldn't use the calculator for. You kind of have to understand this a little bit conceptually, but really it's still just a matter of looking at formulas. But notice how the mu is in between your confidence interval. So if you're concerned about that, so whatever it is, a lot of the times you might be concerned. You might be asked, what is the confidence interval for some value mu, given that we have 95% confidence? or something like that, right? So in that case, what you would do is, if you're asked, say you're asked, and this, I was asked this on the FE exam, and I think I got it wrong. Like, what's the confidence interval for 95% confidence such that given mu, right? So then all you would have to do is realize, okay, well, my interval is in between these. And I don't know why I didn't see it on the exam. I might have been tired or something. But it's basically this. You're saying, well, mu is in between these. And by the way, mu is just X bar. I don't know why they have it differ. But yeah, the fact that this is the case means that our interval is simply just, as long as we're given sigma, n, and z, then we're good. So the only thing we have to do is for the most part, you're given x, alpha, and n, which is just mu. Then just find z alpha over 2. So what is z alpha over 2? Well, you don't even need to use tables for that. If we're saying it's 95% confidence, then it's simply this number. It's so simple. It's just 1.96. So all I had to do was know that basically what they did was they said, okay, what is it? It's mu plus or minus something which we need to find. And all that is it's just this thing and this thing. And it's the same number. And so all I had to do was use the given sigma and n, and along with 1.96, and I got it. So I actually made a mistake on that on the exam, but make sure that it's that simple. Make sure that you understand that you're able to do that, because on the exam you may not be aware of it, and you might totally overcomplicate it and think that you need to use tables. So hopefully that helped. Let's move on. Anyway, so now here's an example for a random data statistic. I just felt like I wanted to include this so you could see the simplicity of of using the calculator. So again, the moral: use calculator, because we want to make sure, because we want to go as fast as we possibly can. Notice how you have all these numbers. We don't want to make our lives complicated. So the calculator will answer each problem. So as long as we just put in our numbers. So go ahead and see the video for the result. Okay, so I went ahead and put in all the numbers. There's 23 numbers, as you can see, that I needed from that whatever we're asked. And now I'm going to go to stat reg, and then I'm going to go to 1var stats. And I'm just going to go ahead and use L1 to calculate. And so we're given, not only are we given our x bar, which is the mean, we're given the standard deviation. And by the way, the SX is the population, and then, or no, that's the sample, sorry. And then the sigma is the population. So if you could see, is the population standard deviation. So it just gives you everything that you need. And yeah, so anyway, oh God, thank you for watching. So as you can see from the video, the mean was clearly x bar equals 740.4. And then the standard deviation, this one, it might be a little bit, a little bit more ambiguous, because, yeah, the numbers, I think I might have been wrong if we just think about it, which one should it be? 549 or 550 or 538? Well, it should be the one that's actually, if you're just finding the standard deviation of the population, it should be the one that is smaller, right? Why? Because you're dividing by a greater number. You're just dividing by big N. That's what it says in the formula, right? Let's go back. So if we go back all the way, we see that the population is divided by big N, so it's going to be a smaller number, and thus we know for sure that it's going to be a smaller number. It's going to be 538. Now, as far as the median goes, we kind of just have to so median is 513. I should also provide that. I actually didn't know it provided it until now. So let me show you on the median is also showing up. It just may not be obvious. Which is right there. If you just keep scrolling through, you'll see what it provides. It provides the minimum, the first quartile, median, third quartile, maximum, so on. On a video. Anyway, let's move on. Yeah, that's the main idea. Just use a calculator. So, okay, now we're moving on to fluid mechanics. So with fluid mechanics, we generally want to focus on fluid properties, and then also things related to pressure, fluid statics, fluid dynamics, and pretty much basic ways you can apply it to hydrology. Now, and that will include the Bernoulli equation and basically discharge formulas that we don't have to actually know how to derive, but just be aware where they are in the handbook. So let's move on. So we start with this very horribly notated set of stresses, which describes a fluid element. So this first, the top one is actually describing the normal stress of a fluid element if we were to think of it as if the water is flowing. So technically the tau n in a normal way or in a usual way is sigma, is usually represented by sigma, which is minus p. And then this tau, I don't even know, tau t is normally represented by just tau, which is the shear stress. And I'll call that the shear stress. I'm sorry. The normal stress, just that confused. And then this is the shear stress, which is equal to mu times dv, which is the velocity of the flow at some given point, divide dy. So this is one-dimensional flow. So we assume that it's just flowing in one direction with respect to the profile. So you might think, well, it could flow in various ways, but we're going to be assuming that it's going to flow perpendicular to the surface, and I'll write that out what that means. But without, in any case, at any rate, the shear stress is typically given by this equation, and this is called Newton's law of fluids. And it basically means that the shear rate, the shear stress is proportional to the shear shearing strain rate. So this is called the shear strain rate, or something like that. You might see that on the exam, and they'll ask you a conceptual question about that, and they did for me, and it was just saying, okay, well, what's Newton's law of fluids, and then it just said that the shearing strain rate is proportional to the shear stress, and I just chose that and I got it right. So anyway, why don't we move on? This is all we really need to know about that. Other than one other thing that I might want to propose or sort of go over too is that it's basically applying a fluid or a stress element in which we assume that there's a surface, like I was talking about, and that you have a boundary condition being that it's basically bedrock and it can't float inside, although it can, but for our purposes it doesn't, and that the fluid, and this is kind of like a elevation section, if this is y and that's x, then the profile of flow is going to look something like this. In other words, at the boundary condition, V to be equal to 0. So that's, but then it's, at the top, it's just V naught. And so this is, although the profile could be of any variation, this is what we mean by one-dimensional. Because obviously it's not going up at an incline, it's perpendicular to the surface, and it's also not trying to twist out. It's just going in one direction, and we expect some arbitrary profile. So this is an arbitrary profile of flow. So but typically it's going to be linear, and so dv dy in that case, if it's linear, is a constant. Although that doesn't mean that the equation is linear, because obviously the equation for shear stress is still linear, because the relationship between velocity and the distance from here, because we know that at this point this is y equals 0. And then we could say this is y equals h, if this is h, right? The shear stress is still related linearly to the change in velocity and the change in or to the strain rate. It's related linearly to the strain rate. So although you might have dv dy could be x squared or something like that. I mean y squared or something like. Something like y squared or something like that, in which case you might have a parabolic profile. It's still, the strain rate is still linear. So that is a nuance that you probably should know. Okay, let's move on. I'm going to get rid of this. And you're going to start to see that right now, what that means. So the next thing that we go over is called the power law, and it generalizes that idea that I was saying about the equation being possibly nonlinear. So this tau being equal to k, and remember this is tau, this is not necessarily tau t or tau f, whatever it says there, because tau is the general way to notate shear stress. So it's basically saying that the shear stress need not be linearly related. So this is the non-Newtonian if n is not equal to 1. So whereas before it was, if it was linear, if the strain rate was linearly related to the shear stress, then then it would be called a Newtonian fluid. But this time it indicates a possibility that the fluid may not necessarily be Newtonian or linear. So if it was nonlinear, there's a couple of things can be described by that, which is certain liquefiable, or I should say liquefied soil can be considered a non-Newtonian fluid. And just basically anything that looks sort of like a solid but is a fluid can basically exhibit non-Newtonian mechanics or properties. And so you could start to see that in many ways, but I'm not going to go over it too much. But basically, the fact is that if it's not linearly related to the strain rate, which is dV dy, then you're basically then it's not Newtonian. So, and you can look up manifestations of that, but I'm going to move on. By the way, I should go back and state that if it was not a Newtonian fluid, then the K there is different. It's not K, it's mu, because if this is Newtonian, then that means that mu is specifically called the dynamic viscosity, and that is a key idea, a key concept, key property when we talk about fluids in general, or Newtonian fluids in general. And you'll see that throughout the course if you ever take one, but particularly you're going to see that throughout the presentation. So just keep that in mind. That's called the dynamic viscosity. So let's move on. So now we're going to focus on sort of an application to the Newtonian shear stress shear strain equation. So here it says, for a thin Newtonian fluid film and a linear velocity profile, Vy is equal to Vy over delta, and delta is going to be the thickness of the layer. So we just say that this is the thickness, and this is just the distance above boundary, as I described earlier. Probably shouldn't have deleted it, but anyway, this is, and then obviously this is the velocity of whatever you have. So, well, I should say this is the initial velocity. So it's the velocity at top or surface of water, of liquid. So, yeah, earlier if I indicated that it was water, I meant to say fluid, because in general these should apply to any fluid. Liquid. So basically, what this means is basically what I was saying earlier, but instead assuming that it's a linear profile. So specifically, this is a linear profile where this is V, and this here is delta. And so this can describe, sure, it can describe a water flow, but they're specifically saying that this is going to describe a small fluid film in which, this could be oil. Let's see what else. It could be, it's typically like an oil or some kind of, it could be could be like milk, I don't know, just something that is resting on a surface and it is in motion. So I don't know how that can be manifested, but this is the basic idea of what that's about. So it could also have something to do with I just thought of it, kind of like a bubble film. In some way. I don't know how that would manifest, but this is what this equation is describing. And so if you want to go into more detail, you can go ahead and look up in your books or something. But basically, if you're going to use this equation, realize that the most important thing to realize is that dv dy is not computational here, but approximated as delta v over delta y. And so in the case of a fluid film, just remember that you're trying not to get a v of y and then differentiating. You're just trying to approximate it. So let's move on. By the way, I didn't see that on my exam. Okay. So now we're moving on to the idea of kinematic viscosity, and it's related to both the mu and the rho, which are both the dynamic viscosity and the density of the fluid. So, well, in this case, you could say liquid, but now earlier I said that this applied to a liquid only, but I meant to say fluids in general, because it could also apply to air or some kind of fluid. But you have to be very cautionary about it, because it's possible that the particular fluid that you're looking at, it has its own, you could say, reductive property which would prevent you from using this equation. Don't know the specifics, but for the purposes of the FE, just realize that it can apply to every fluid, and if it's flowing, it doesn't have to apply to just liquids, but probably 90% of the time you'll probably see it as a liquid. Anyway, let's move on. Saying about the viscosity, about the kinematic viscosity, this is the most important idea, because remember earlier I said this is called the absolute dynamic viscosity, right? Well, for the kinematic viscosity, which is equal to the dynamic viscosity over the density of the fluid, basically, if you have only this, then you can calculate what we call the Reynolds number, which is, I believe, Vd over the kinematic viscosity. And so if you compute the Reynolds number, you're able to extract a lot of information from it, such as if it's a laminar flow, or turbulent flow. And that's important because it allows us to get a better understanding of what's the physics of what's going on. Because in turbulent flow, you have all this friction going on. There's a lot of friction that we may not be aware of at the beginning. And then for laminar flow, it's mostly smooth. So it's like smooth. Oops. And this is rough. So when you're looking at these different scenarios, you want to know about what happens with the flow, because once you get the Reynolds number, you could use a table to determine what these are, if it's laminar or turbulent. And so the Reynolds number has something. It has to do with the Buckington pi dimension theory, and I don't really know much about that, but I just know that it works. So we're going to go over that a little bit later, but let's I hope you understand that this is actually very important. The kinematic viscosity is a very important concept. because it allows us to extract multiple information about the fluid that would otherwise be very difficult to fathom. Important. So remember this for the exam, because especially for my exam I had that, and I think a lot of people will see some variation of kinematic viscosity. Anyways, let's move on. Okay, so for chapter 6 we're going to look at an example. It says a solid cylinder is concentric with a straight pipe. The cylinder is 0.5 meters long and has an outside diameter of 8 centimeters. The pipe has an inside diameter of 8.5 centimeters. The annulus between the cylinder and the pipe contains stationary oil. The oil has a specific gravity of 0.92 and a kinematic viscosity of 5.57 times 10 to the negative 4 meters squared per second. The force needed to move the cylinder along the pipe at a constant velocity of 1 meter per second is most nearly... Okay, let's look at what this is all about. So why don't we have to kind of understand this from a visual point of view. So it looks to me like they're saying, okay, it's concentric and it's a straight pipe, right? So you're gonna look something, and notice how it has a finite length. So first of all, let's just draw the outline of that. So we know that if this is a length of 0.5 meters, and there's basically, they're trying to get you to say, okay, well, the inside diameter is actually, I think this is a mistake, because this should be 8.5 centimeters, and the inner, because obviously the inner is going to be less, right? So there was a mistake. It looks like there was a typo in the solution. Let me just get rid of this. You'll see that was clearly a typo, because I did this problem a while back, and I remember that. Anyway, so although pictorially it doesn't look like, let me get rid of the thickness thing. It doesn't look like the pictorially it doesn't look like the diameter should be that big, but it just is. It's just my drawing. Anyway, so let me just draw this a little bit more with more detail. So if we think of this as if this is a solid piece and it's in between another solid piece, that might have its own thickness, but basically in such a way that you could pull it out. So let's say if so we know that the thickness is going to be basically the radius subtracting each other. Why? Because if you were to take the r out minus r in, obviously you get the distance between one solid and the other solid. So then that should just be 0.25. Now I don't need to derive that, right? I could just say either you could take 8.5 minus 8 and divide by 2, or you could notice that you divide by 2 right away and you get 8.25 minus 8, you get 0.25 centimeters. So you know that the thickness between it is 0.25 centimeters. And so now that we have a pretty good understanding of what this represents, then we can start doing the problem. So we know that what they're asking for is they're essentially asking for the force needed to overcome friction. So we want the force needed if the velocity in between, it says the force needed to move the cylinder along the pipe at a constant velocity. So if the cylinder on the inside is going to be pulled at a velocity of 1 meter per second, then there's going to be a particular shear stress at that point. So what is the relationship between force and shear stress? Well, we know that force is equal to pressure times area, right? And the shear stress is a form of pressure, so it's also the shear stress times the area. So if we were to think of this as if we take the shear stress times the area, then we're good. But how do we get the shear stress? Remember, what's Newton's law of fluids? It's mu. It's that the shear stress is mu times dv dy. And so if we think of the solid on the outside as being the boundary condition, is a fixed what do they call that? Outer solid. Then the boundary condition is a fixed outer solid. Then we know that if we were to take this as if at the edge, it's 0. So this can be approximated as delta y being equal to the thickness minus 0. So you could say that y is 0 at this point, and then y is the thickness at this point, and then you take the change in the velocity to be equal to well, what do we know about this? It means that v is equal to 0 because it's fixed, right? At the outer solid. So we know that that's just 1 meter per second minus 0 meter per second. And that's times mu, which is equal to what? Okay, so far we're left with this equation, correct? It confused you a little bit earlier. This is the dynamic viscosity, and remember, we're only given the kinematic viscosity. I think I might have led you in a bad way on accident, but let's consider what happens. So basically, the fact that we're given the kinematic viscosity, but we're not given the dynamic viscosity, means we're going to have to do a little bit more work. So to get the dynamic viscosity. So the computation of the dynamic viscosity is pretty easy. I mean, it's pretty easy. So let's remember what it is. Remember, the kinematic viscosity is, as we could see if we go back to our, it would be the dynamic viscosity divided by rho. So it's the dynamic viscosity divided by rho, which means that mu, which is what we really want, is rho times v times the kinematic viscosity, which is given. However, the density is not the density of water, but it's the density of the liquid we're given. So keep that in mind. This is not water. So what we have to remember here is that, how do we get the density of the liquid? Well, we're also given the specific gravity, and so that's pretty clear. Whenever we have specific gravity, it's gonna help guide us to how to get the density of the liquid. So all that means is that the liquid density of the liquid is equal to the specific gravity g, and sometimes it's called gs, times the density of water. So then that's just equal to, you should remember this because it'll come up a lot. 1,000 in SI units, and there's all these, all this weirdness involved, but times 0.29 or 92, and so this, I don't remember what the units are, but I always use 1,000, so I know that for a fact this is 920. And we don't need to know, as long as it's consistent with kilograms, meters, and seconds. I mean, you don't need to know the units. So if we're going to go back to this problem, we're going to say that this is equal to, oh, and by the way, this is times, 5.57 e minus 4, because e is, I'm going to use scientific notation. And so I'm going to go ahead and compute that. 0.512. So if we go to here, this is just 0.512, and that's pretty simple at this point, because then it just becomes 5 pascals. And then finally, what we need to do is use this equation. So you can say, okay, now we can finally use this equation, and this will be our final answer. Times, remember, it's 2 pi times the radius, and in this case it's the inner radius, right, because we're trying to find out what the force is at that point. So, but yeah, and so in this case it's going to be pi r, so r in this case is 4 centimeters, pi r square, 2 pi r, because that's circumference, and then we multiply it by the height, which in this case is considered the length, so it's 0.5 meters. And that'll be, let's see, our answer is going to be 26 newtons. And go ahead and compute that and confirm, because that's the answer. That's part C. And now this is considered a relatively difficult problem. I went ahead and gave it because I know that it is a harder one, but I want to see if you can put it all together. Anyways, let's move on. So one last thing about fluid properties is, let's just see, is there's this concept of surface tension. And so for surface tension, you have something called surface tension is a result of cohesion and adhesion of liquid. Typically you have a liquid in a container, right? And the liquid in the container. So you might have a container like this, and then you're going to have a meniscus in some way. And the reason why this is happening is because at the particle level, you have something that looks like particles on the solid piece sticking to the liquid piece, and they're sticking to each other, right? But then on the other hand, you also have, and this is called adhesion. And then on the other hand, you have liquid particles that are pulling on each other and trying to make it go that way, if that makes any sense. So this is cohesion. And so as a result of all this, this is the reductive version of the engineering way of looking at this. Because the engineering way of looking at this, they only concern themselves with how they think. So in other words, how they think has a lot to do with forces and Newton's laws. So we're going to be using Newton's laws to actually understand what this means at the engineering level. And so let's see if I added anything else. No. Anyway, so the way that you understand what this means has less to do with the reductive version and more to do with the engineering version. So why don't I get rid of this? We're going to move on to the engineering version of the explanation. So the engineering explanation is that for this formula is that you have some kind of liquid, and it could have an indefinite. If it's in a container, it can have an indefinite way of extending. Right? So, but the whole idea is that you have this liquid, and we just assume that we just have it in the beginning, and that we essentially have a section here where it contributes to weight. And so the weight, if we look at it as assume a circular container, because a lot of times it is, then what we do is we say that the weight is equal to, or you can say the magnitude is the density, because if it's assumed to be linear, times the height times the cross-sectional area, because the area is the same. So then that's just rho h times pi r squared. So if you look at it this way, then you know that the weight is going to be that way. But then if you zoom in on this part and you look at the mechanics, what you're really seeing, like we said earlier, is it's a reductive thing, but not really reductive, because we're still looking at it at the engineering level. Because we see here that there should be a tension here and a tension here. So this is tension, and this is also tension. They're assumed to be the same, and there's an angle. Actually, this is the wrong angle. The angle is usually taken, for some reason, it's taken at the vertical, and they're assumed to be the same. This is called beta. The angle that the tension makes, the film at that point makes with the vertical. So if we were to look at it that way, then we can see that the sum of the forces in the y direction is simply 0. But that's also, the sum of the forces is also the weight, which is rho h times pi r squared. And then it's also, we can call that a minus if we're going to say that's minus. And then it's going to be plus, because the weight is just completely vertical. And we could say, this is y, x. And then we could say that we add that to the tension times the so tension times the what was it? Would it be the cosine? Well, let's just think about it. The cosine would be this times whatever is here, so that would be the vertical. So it would be the cosine of beta. Now this is going to be equal to 0. But now the tension is easy to compute because we know if we have what we call the sigma, then that's simply, by the definition, is F. So that would be F, which is just equal to this times L. But L is the length, so that's going to be pi times 2 pi, sigma times 2 pi times the radius. So because that would be the circumference, right? So if you multiply, this is per length times the circumference, then you get the overall tension. So then that would mean that minus rho, or I should say plus rho h times pi r squared is equal to this times 2 pi r cosine. And so if we're going to continue on with this, then we see that that if we want to know what the h is, then that's just simply sigma times, and remember the pi goes away, one of the r's go away, so that you're left with cosine of beta times what else is there? Is there a pi in there yet? No, pi goes away, so sorry. The 2 is left over, and you basically have nothing else left on the top. So then you have rho. What else? We have one r that's left, and so essentially you're left with this. But remember, what is d? D is r over is 2 is d is, or r rather, is d over 2. So then this becomes 4 pi cosine of beta divided by rho times d, right? So the rho, though, is in here, they're almost like, this is almost identical to this, but the only difference is I think what I messed up on, and I know my notation is bad, but I didn't mean that. I meant to say that this is the unit weight. Because the unit weight is basically the total weight divided by the volume. I meant to say the unit weight. I'm sorry about that. This should be the unit weight. That was a screw up. But I often get the two mixed up until they're relevant. So it's fine. This should actually be rho. And I don't know what I'm going to do about that, but I just messed up partially on here. But because rho is technically just the it's the mass over the volume. It's not the weight over the volume. So I often get the two mixed up. So technically the rho times g is the unit weight, but I meant to put that. So that's that, and hopefully you can forgive me for that mishap. But this is how you would derive the equation, and so you would end up with that. And that's important because if you get a conceptual question where it's no longer circular, then you have to rederive it. You may not get that, probably won't. Anyway, thanks for watching. Let's move on to the next thing. So now for chapter 6, let's see an example of that application. So it says a capillary tube 3.8 millimeters in diameter is placed in a beaker of 40 degrees Celsius distilled water. The surface tension is 0.0696 newtons per meter, and the angle made by the water with the wetted tube wall is negligible. The specific weight of the water at this temperature is 9.73 kilonewtons per meter cube. The height to which the water will rise in the tube is most nearly, and now that you understand the concept, we see here that it says 3.8 millimeters in diameter. So it's obvious that we get to use the equation, right? So whatever we derived earlier, we just get to use it because we know it's circular, right? So 4 pi cosine beta times, and then divide by, and then let's just see, obviously, and then obviously this goes to 0 because it doesn't make an angle. Remember, it's I'm sorry, not 0, that's 1. So this is just simply 4 times